Uh, Fantastic. Well, welcome everybody. I'm pretty excited about tonight. So much has gone well with James Webb. It's been 64 days since the launch, and God, everything has just been almost picture perfect. And I'm still adding slides, even just a couple days ago, of breaking news of new instruments being turned on and different events happening. So I will take questions at the end of the presentation. I don't have an opportunity to see, or it's hard for me to pay attention to chats. In fact, let me see if I can actually. So if you don't mind, if you can save your questions to the end, and I'll be happy to address them. So what I'm going to do tonight, may have been just a little bit too ambitious. There's just so many things that have happened since the launch date on December 25th. I do have NASA published just a really cool little quick 1 minute and 20-second video on the deployment as a function of each day that goes by. So when we, I'm going to play that video, and then we're going to talk about some interesting aspects of where James Webb is at. We talk about it being orbiting around L2. Well, that's almost true. It's not actually at L2. It's at what we call L2 prime, and I'll explain what that is all about. And also we've turned on some of the cameras. The workhorse camera is actually alive and well, the near cam, and it's the one that's going to help us do all of the segment alignments. We're actually have already started those segment alignments, and I've got some really cool pictures of that progress. And then just a couple days ago, we turned on the fine guidance sensor, which will help stabilize the image. It's literally very similar to what we do with a guide star. Webb finds a guide star and samples its position, and then gives feedback to yet a fourth mirror that's just right before all of the sensors, and gives us that final tuning of the image before it hits any of the sensors. So I'm just going to play this. So sit back and relax for about 1 minute and 20 seconds. Before I do that, there's just a great website that I recommend folks to go to if they want to kind of get literally a day-by-day update of what's going on with James Webb. It is web nasa.gov. I've got the link shown here. You can pick it up from the recording. I'm just going to quickly go to the website right now, but it's got a lot of cool information in there. No pun intended. All the temperatures that we're trying to to achieve. Right now, on the dark side, we're actually down to like 46 degrees Kelvin at one of the number three location that's on the instrument side. So good progress on cooling the instruments, but then down below is basically the current events, things that are going on right now with Webb. Lots of cool links to videos and blogs and that type of stuff. So and news items. I go here every day to kind of get an update along with my regular NASA briefings, but this is just really an excellent site. And so let me jump out of the site. And I think I went too far. And here we go. Okay, so all right, so let me just run this video, and then I'll pick up after that. Just gives me chills every time I see that. So what's amazing, as we all know, there was over 340 different failure mechanisms involved in that unfolding, and we were actually able to retire all 300 plus failure mechanisms during the course of those 29 days. So we have now arrived at what we call the L2 location. And one of the first things we did was to kind of take the mirror segments out of their stowed position. And that little figure up in the corner there shows when they're stowed, they're at minus 12.5 millimeters, just a sensor that tells where that segment is at. And the actual deployed mechanism is at 0 millimeters. Now, one of the things that caught a lot of people's attention pretty quickly was that after all of the segments were deployed, there seemed to be a couple days delay on, if you notice segment A6 and A3 did not deploy. And so interesting story here, there was actually two faulty position sensors, both on A6 and A3, that was actually discovered pre-launch. And a big executive decision was made. Do we replace those sensors, or do we come up with a plan B on how to measure the position of those two segments? And as it turns out, the decision was made to just go with a plan B post-launch. What was involved there was that there's actually two coils that are associated with this position sensor. And they use those two coils to kind of measure what the differential temperature is at that location. And kind of neutralize any temperature effects in the accuracy of the position sensor. Well, in both those segments, one of those coils were defective. So we had two bad coils, but the engineers were able to work around and come up with a software fix that just allowed the sensor to be pretty accurately read by just using one coil. And with the assumption that once we got out there in outer space and we got the Webb in the shade, that there wouldn't be that big of a temperature differential on those sensors. And long story short, those A6 and A3 have been deployed, and we're getting very, very accurate measurements on where they are located. So we are, as I said, launch plus 64 days. We are right almost smack in the middle of focusing all of the optics, getting all 18 mirror segments focused and essentially aligned to become one telescope. Presently, we have 18 telescopes working in orbit, and I'll actually go through the alignment sequence here in a little bit. And so we have about 54 more days of focusing. So anytime any one of us complains about focusing our telescopes and it takes a couple minutes each night to refocus, think about James Webb and the months that it's going to literally take to focus that telescope. So one of the things we kind of casually talk about, we actually make a big deal out of the fact that Webb is orbiting a point called L2. That's a stationary point that allows us to stay in lockstep with the Earth as it rotates, orbits around the sun, and stay in a. Did somebody mute their speaker there or microphone? And so what we've been telling folks is that we're at L2 and we're orbiting around L2. Well, that's almost correct. So I'm going to go into a little deeper dive about where James Webb is actually located and why we're orbiting around that point instead of actually being at L2. Okay, so this is just a real cool little short video that shows that orbital plane of L2, the halo orbit, as we call it, around L2. Now, there's nothing at L2. That's an empty place in space, but orbital mechanics does allow us to orbit not only objects, but literally center of masses or Berry points, such that we don't really need to have a particular object. We say that the moon orbits the Earth, though that's not exactly true. It actually orbits what's called the Berry point, the center of the mass of the two objects. In the case of the Earth and the moon, that Berry point is actually inside the Earth. So it appears that the moon is orbiting the Earth, but it's actually orbiting the center of gravity between the two bodies. Okay, so what's wrong with being at L2? It seems like it's an ideal spot. It's always mostly in the shadow of Earth, and it moves very nicely synchronously with the Earth. But have to remember, Webb is in fact a solar-powered spacecraft, and if we were at L2, we would actually lose about 60% of there's enough shadow by the Earth, that Webb would actually lose about 60% of its solar power. So that alone tells us that we've got to move it away from L2. The other thing is, if we were precisely at L2, there are Coriolis forces that would actually cause small vibration or oscillations around L2. And we're all about conserving fuel, because remember, the fuel is the limiting factor on how long James Webb is going to last, because we do have to fire thrusters to keep station, keep the orbit intact. And if we were right at L2, that vibration would actually cause us to use far more fuel. But probably the most critical thing is the fact that L2 is referred to as what's called a metastable point. And I'll explain that in detail. It's very hard to maintain a stable orbit at L2, and I'll show you all the reasons why in a second. And the other really dangerous thing about L2 is, remember, Webb only has thrusters on the sun side of the shield. Webb can only move in one direction, and that's away from the Earth. And so if by any chance that Webb got past L2, the only way it could get back to L2 is to actually rotate completely around and put what was super cool down to 30 or 50 degrees above absolute zero, rotate into direct sunlight, would actually destroy all of James Webb. It would be absolutely catastrophic for the seals, for the instruments, everything. And so that's reason alone. When we actually launched the Webb, we always had in our minds that we would always come up short. We weren't going to go for the hole. We were going to putt and lead up to the hole and not actually get to L2 because of that danger of going past it. And then finally, if we're actually in line with L2, that's almost a direct line to, the Earth is directly in front of the sun. And there would be a tremendous amount of inline radio interference from the sun that would actually affect our communications. Okay, so how are we going to fix this? So we refer to L2 as being a metastable, or I've seen in a lot of illustrations, we call it the L2 saddle. And so if we look at a saddle, and we represent L2 by this figure, and then let's assume that we've got this, because we're in outer space, right? We've got this frictionless surface, and we're trying to balance a marble or a ball right smack in the center of that saddle. Well, that's going to be very tough to do. The slightest movement in any direction. Now, of course, these contours represent gravity wells, right? And so if Webb moved to the left or to the right, that's fine. It just comes back to center. And if it rolls forward, that's towards Earth, no big deal either. We can always thrust her back. But if we roll off the other end of the other side, then the entire mission is lost. Okay, and so if we take a kind of a bird's eye view of that L2 position, three of those vectors, the top and bottom orange vectors and the left blue vector, fine. But that right blue vector basically is the catastrophic position. So at all costs, we need to avoid being in that position. So how do we fix this? All right. So what I'm going to do is and I apologize for the next 3 minutes. We're kind of going to go into Geekville here, but some of you will appreciate this, and others will, if they just have a little bit of patience, we'll get through it. And so what we're going to do is we're going to place Webb right at L2, and then we're going to jump feet first into a frame of reference, an actual rotating frame of reference. Our physicist friends in the audience would refer to that as a non-inertial frame of reference. All that means is we can represent forces around James Webb in terms of these force vectors, and we can actually talk about a centrifugal force, which some of you probably know is a pseudo force. It's not a real force. But when you're actually inside this rotating frame and in a non-inertial environment, the centrifugal force is useful in looking at balancing forces, even though it's not a real force. So we're going to put so the hallmark of L2 is that the gravitational force in yellow there and the gravitational force of the Earth balance nice and equally to the centrifugal force on Webb at L2. Now, in the ideal world, and if everything was no Coriolis forces and no other acting forces like the influence of the moon, and this is a gross simplification, of course, but there's so many other factors that actually make being at L2 not as simple as this diagram. But this gives us our first approximation of what's going on. So what we're going to do is, because we can't be at L2, so let's just move James Webb up. Seems like a simple solution, but it doesn't really fix the entire problem, because now if we move James Webb up from L2, it's actually moved farther from Earth, and so now there's an imbalance. Members, the real dominant, balance of the sun's gravitational pull and the Earth has now been offset. So now literally the centrifugal force actually because the force from the Earth has been reduced, that centrifugal force has now increased. And that, again, is going to pull Webb into Doomsland on the wrong side of L2. All right, so what we basically can do here is well, let's break that gravitational force of the Earth into its components, its X and Y components. It's just a little easier to see what happens, and the net result is Webb would in fact drift to the right of L2. All right, so easy fix. Let's just move Webb a little bit closer to Earth at its elevated position above the center line, and voila, we can balance that centrifugal force again. Unfortunately, we're still left with that little Y component there, and Webb would then eventually drift down back to the center line, and essentially we would start to decay into a bad situation again. Easy solution to that is to generate yet another centrifugal force, and that is to shoot Webb coming out of the screen here into an orbit, and that would generate a halo orbit with its own centrifugal force that's going to offset that Y component. Oh boy! Again, I apologize for all the geekness here, but this is kind of a snapshot of what's going on, and so. In reality, when we kind of said on the news that, oh gosh, we're at L2, we never actually got to L2. We got to L2 prime, And at that point, in front of L2, we did our final burn, the MCC2 burn, and went into this huge elliptical orbit around L2 prime. And this orbit is larger than the orbit of the moon around the Earth. Literally, it takes 6 months for Webb to make one complete orbit around L2 prime. I'll just show you some profiles of the orbit. And this is, I promise, this is the last orbital mechanics slide, and you can see that even the geometrical center of this highly elliptical orbit is that L2 prime, but relative to L2, it's 155,000 miles at one point to almost 500,000 miles from L2. So that's where James Webb is at. It's so you can tell your friends it's not at L2, it's at L2 prime, and is doing well, and it's going to take literally 6 months to make one orbit. Okay, so I'm sure there'll be some questions maybe about that at the end of the talk, but so let's brighten up or put a new light on things, and let's talk about the NearCam, the workhorse camera on Webb. Was the first camera to be turned on, and there was just a round of applause for all the scientists and engineers when they actually got what we call first light out of this near infrared camera. And of course, I don't know if you've all seen this. This just ripped through the internet. It was posted as Webb's selfie. This is not an external camera that on an arm or a boom or something that took a picture of the array. This is actually the NearCam camera itself, and they included a special lens that they, for just this purpose of looking at the alignment of the segments. So they put a special lens in front of NearCam, and it was actually able to see the entire 18 segment array. The one that's of the brightest was fortuitously perfectly pointed at a very bright star, so it lit up that entire segment. Remember, we've got, at this point in time, we've got 18 different telescopes, and so but we turned Webb towards a star, and we proceeded to take the first picture. And of course, our expectations were that we were going to see this star 18 different times, or in 18 different places on the NearCam sensor. So it's a 6.9 magnitude star, but this star will go down in history for sure. It's about 259 light years away. It's a little cooler than our sun. It's a Class K star, but that was the first target. So we spun up the reaction wheels and literally pointed Webb towards that star, and just a little reminder, the field of view of these instruments are actually pretty small, and so the NearCam field of view for this first picture was only 2 minutes. 2.6 minutes by 2.6 minutes, and in a minute is 1/60th of a degree. So this is a pretty small field of view, and so it turns out that we had to take hundreds of pictures. So the backstory is, and I circled one particular field of view, but in order to find those 18 versions of that same star, we had to do a mosaic. And I thought this was awfully cool. Some of us have done mosaics, not of this magnitude. I've done some 4x4 mosaics, but nothing that was, so grandiose as this one. But you can see we had to do this big matrix here, and the stars were actually spread out over many different positions of Webb's field of view in order to capture where each of those stars were at. So that was pretty cool. This was the picture that was published that got all the hoorah on the internet. This is a little sidetrack here for NASA. NASA initially said, no, we're not going to show any intermediate images. We're just, we don't want to get the public alarmed. But they kind of, under whatever kind of pressure, decided to release this very first image. And again, this is a mosaic of many fields of view in order to figure out where the 18 stars or 18 versions of the one star is located. And so the next thing to do was to in fact identify which star was which. And I'm going to use a scientific term here. We jiggled each mirror and watched to see which star would jiggle in the mosaic, and we had to obviously do that 18 different times. So by jiggling each segment, we were able to come up with a map and be able to label, and the fold out wings of the mirror, the parts of those three segments that were folded behind, were kind of fell where we thought they would. Pretty much on the outside, except for these two segments. But this was still pretty hard to work with. But now we had everything identified, and at this point, we can actually now bring into play all of the activators. Every segment has 7 degrees of freedom. Literally, each segment has 7 activators in the back, and so we can tip, tilt, roll, and XY position every segment, and also change its curvature. This central activator here actually has spider legs that go out to the ends of the segment, and we can actually change the curvature of the segment. So having that control, and that was another major milestone, is being able to verify that all of these activators on the segments work. Since we did that, and since we did have identification, we then could literally align the mirrors such that the mosaic represented the actual spatial positions of each of the segments. So it's just getting cooler and cooler as it's going. The next step is to actually do what's called a global alignment. But in order to do that, we have to use one of the imaging tools. And this is a kind of a tool that we amateur astronomers actually use, and in some form. And so it's called image phasing, and we use something called a PSF, which is a point spread function. And that's just a fancy term for if you plot all of the light coming from that particular star. As you saw, some of them were spread out and elongated and so on and so forth. It's really nice to have a graphical representation of that. And then as you move all of those actuators on the segments, you can actually bring all in all of that peripheral spread of the star, and use this tool to initially move that segment in literally millimeters. And then finally, when you get down to what we call fine phasing, those segments are moving less than 10 nanometers in positioning. And so we're going to use this tool to globally align all of those stars. And so far we haven't converged them yet, but we are going to try and get the best focus possible before we start to converge the stars. I just grabbed some of the intermediate images as we're going through various stages here. And typically what we do is defocus the star, it gets real big, and then we bring the mirrors or the lenses back in the other direction. And so they go through, these are pretty spectacular looking diffraction patterns that Webb is going through. So I just grabbed a few, and then finally, as of 2 days ago or 3 days ago, on February 18th, this is kind of where we're at. As you can see, we still have a lot of work left ahead of us in doing the alignment, and so I'm going to, let me just do something here. Let's see here. Oh. Oh, okay. I thought I could bring up another screen here where I could see if there was any comments within the image icons of the participants, but the way I've got this presentation mode set up, I can't see everybody when I'm sharing like this. But anyway, this is where we at. This is where we're at. B6, A1, B2, B1. Still got a ways to go. In fact, I think we probably have another month's worth of work before we actually go to the next step. And the next step is what we're going to be calling segment stacking. Remember, this is all going to happen over the next 54 days. So nothing happens very quickly on Webb. And so after we get each segment aligned to the best we can, we're then going to start to merge and try and reduce the number of outliers until we're all the way down to one perfect star. And literally from where we're at now, doing the global segment alignment, and then this merging step is going to take us another 54 days. So we won't see one telescope for quite a while. Okay, one of the last topics I'd like to talk about, and there's been a little bit of controversy about the resolution of Webb, and I thought I'd clear up a few things about what we mean by resolution and what we can expect. I'm not trying to lower expectations or anything like that, but I do want to emphasize James Webb's strength is in its spectrographs, right? And so literally, when we start going and looking for those first galaxies and the first stars, those objects are so redshifted that we're going to be in the near infrared, or not near infrared, but mid infrared, and even farther out. And we're going to talk about how those extra, that lengthening of the wavelengths basically is going to kind of really hurt the resolution of Webb when it comes to visual type images. And so there's been a lot of controversy, a lot of stuff going back and forth, and so I want to just kind of clear the air and lay the expectations. and do some comparisons to Hubble, where we're comparing apples to apples. First of all, let's define what we're talking about. We're actually talking about something called an angular resolution. That's our ability to separate objects or details. And so what we are basically trying to determine is what is the minimum angle here where we can actually still see two stars, for example. How close can those stars be, and we can still see them as two stars? At some point, of course, they're going to be so close together, the angular resolution won't be great enough for us to even determine that there's two stars. But we have a way of measuring that, and so we can actually calculate the angular resolution on a telescope fairly easily. And what we're essentially doing is we're looking at the intensity plots of let's just say a double star image here, and we use something what's called a Rayleigh limit that basically defines what kind of a dip is necessary between the intensity of two stars in order to still say that there are two stars here. And so this limit is basically defines in our equation for angular resolution the coefficient. But what's really important is not so much the coefficient here, but I just want to get the point that angular resolution, how well we can distinguish and separate details in an image like two stars, is not only a function of the diameter of the telescope, and you can see that the aperture of the telescope is in the denominator, and that's a great place. So the larger the telescope, the smaller that angle is going to be that we can distinguish between stars. But on the flip side, we can't ignore the numerator, which is the actual wavelength of the light that we're looking at. So the longer the wavelength, basically the larger that angle is going to become. And I'm going to show you how that affects us on James Webb as we move into the mid-infrared. Okay, so if we take just a standard telescope, amateur telescope, and we throw in some typical numbers of a wavelength, someplace between blue and green, kind of someplace in the middle of the visual spectrum. And we run through the numbers and do all the conversions. We measure everything in what we call an arc angle, and so that arc angle can be in degrees, it can be in minutes, and it can be in arc seconds. And arc seconds is our smallest unit that we use for this measurement. And one arc second is 1/3600th of a degree. And so it's extremely tiny measurement. So if we take a couple of these are three examples, kind of a high-end observatory, 1 meter telescope, an amateur telescope at about 200 millimeters, and then this is a cute little Cassegrain telescope. It's only 24 millimeters, and this is the kind of design that's used on these CubeSats that you hear about, or these little satellites that are released from major satellites, and that can actually go out and take pictures of their parent that they released, or they have their own experiments. But these are only like 24 millimeter telescopes. But threw that in as an interesting comparison. And as you well expected, as remember, we said aperture is everything. So with this 1 meter telescope, we clearly can see two stars that are like 2 arc seconds separated from each other. Pretty small, very small angle between the two. And even with a 200 millimeter telescope, we can easily see the two stars. But with our poor little 24 millimeter telescope, there's just no way the resolution is not there. A little easier to understand. Again, here's for our planetary folks. Again, aperture is everything. Here's our Saturn, our 1,000 millimeter telescope, 200. As you can see, the resolution is starting to drop significantly. And at 24 millimeters, one can't tell that that's Saturn or what it is. So that's one aspect. So clearly Webb has the advantage over Hubble with respect to its mirror. I mean, the diameter of Webb's mirror is just a little over 6.5, 6.6 meters. Hubble was only 2.4. So just in aperture alone, Webb is going to have about 2.6 times, 2.7 times the resolution, just based on the fact that it's a larger aperture. So already we're ahead of the game. Now, if we want to compare pictures, and this is I want to really emphasize this. If we're going to compare a picture taken by Hubble spacecraft and James Webb, and I'm sure we're going to be doing that in the future, we have to make sure that we are taking the pictures at comparable wavelengths. Remember that numerator where the wavelength is in the numerator. And so if we have dramatically different parts of the spectrum that we're looking at, we're gonna falsely represent the comparison between the two telescopes. And so you literally Hubble can actually look a little bit into the infrared, and certainly James Webb starts at the infrared. And so if we're going to do any comparisons, this is where we have to do the comparison. And so some pretty spectacular results at the near infrared. You got to remember, Hubble is meant for ultraviolet and visible light, and it kind of sticks its little toe into near infrared. But in comparison to James Webb in that same wavelength in the near infrared, say like around 1,000 nanometers, Webb is going to shoot the socks off of Hubble. Just not only in that 2.6 aperture increase in resolution, but the infrared camera on Webb has 16 times more pixels. And the other thing that Hubble can't do is it doesn't cool its camera to the extent of the cooling by James Webb. And so if you add all those things together, there is going to be a significant improvement in what the images are going to look like relative to the resolution between the two cameras. Okay. Again, just as a reminder, now when we go and start looking in the mid-infrared, like we're going to be out maybe at 15,000 nanometers or 15 micrometers wavelengths, this numerator is going to be really very much in control. So once we move from this overlap region here, and we start moving out to like wavelengths around 15 micrometers, micrometers, the resolution on James Webb is going to drop off precipitously. Okay, and so in fact, literally at 15 microns, Webb's resolution will be no better than that of a amateur telescope, running in the visible light spectrum at like 0.5 microns. Okay, and so you hear this come up all the time, but when we're working at this level in Webb, we are going to be taking spectra and not pretty pictures. Okay, and again, just to wrap this up, if I look at the difference between the visible range at like maybe half a micron versus 15 microns. These are not images that we are going to display to the public. Okay, Leslie, boy, and I think I did it. I mean, I've got five minutes left. I haven't been able to see anybody's faces because I've got this presentation screen up, so I'm using two monitors for the PowerPoint. Hopefully, I can drop that down here in a second. But lastly, again, breaking news: as of 2/17, we actually got the fine guidance system up and working. Really a cool timing for this because this is actually going to basically make our alignment process even more accurate because what the FGS does is it identifies a guide star and locks onto a guide star and samples its position 16 times a second. Or no, I'm sorry, once every 16 milliseconds. It'll sample that guide star, and then every 3 seconds update the final what we call the steering mirror. Just kind of show you where that's at. So the last mirror just before the light from our object hits one of our sensors or spectrographs, this mirror is adjusted to compensate for the movement of the guide star. So in terms of our local astronomy friends, this is an auto guiding system, which is really cool. And this started working just 4 days ago, and they are now actually using the fine steering mirror, and along with the guide star to in fact do all of the segment alignments. So I think with that, what I'm going to end here and then open it up for questions. Next time in about 2 months, I'm going to be doing a NASA presentation, kind of a deep dive on all of the instrumentation. So we're gonna tear apart the instrumentation package, look at all the characteristics of the cameras and the spectrographs and the coronagraphs and the slits, micro slit system. And so we're going to do a deep dive next time into Webb's science instruments. And at that point, I'm opening up for questions, and I'm going to see if I can get your faces back. Yeah, unmute. Feel free to ask questions. I'm trying to see how I can actually see everybody.
Not so much a question. This is Mike.
Oh, hi, Mike.
It's not Kathy. It's me, Mike. It's my wife's name. But one thing that you commented on, which was totally surprising to me, was the distance of that orbit around L2. I had no idea it would be so big like that. But I guess that gives it a lot more sunshine out there too then. So.
Oh yeah, no, there's at that distance. Plus, it actually also improves the communication. Because we're now not directly in line. The high gain dish is now pointed down towards the Earth, and not in direct alignment with the sun. So there's going to be far less communication errors as well.
If I could ask a quick question,
Sure.
picturing the dynamics of all that orbital movement out there and the fact that the moon is going to be in between there as well on an occasion, I would imagine it's going to cut in between the, well, I guess it's never going to be pointing towards the Earth at all. All the pictures are going to be looking away from the Earth-Moon system. So I guess in that regard, the moon's never going to be an issue as far as any kind of signaling.
Oh, no, but it is an issue. Remember, the simplified diagram, force diagrams, I was dealing with just the major forces. But no, the Fine Guidance Committee, the one that make the corrections to Webb's orbit, they not only take into account the moon, but also Saturn, Jupiter. they go all the way out nearly to the end of the solar system. Has effects on Webb, and then of course every time we point Webb is going to perturbate the orbit, and then literally those reaction wheels. Remember. That points Webb, we've got this big solar sail out there, so we're getting bombarded with photons as well, and so we have to correct for the solar pressure on Webb, and so the other satellites that are like neighbors of James Webb, like Gaia, is orbiting around L2. We have to do station keeping on Gaia maybe twice a month, 2 or 3 times a year. And with James Webb, we actually have to give a little kick of the thrusters every 21 days to adjust. Part of that is to unload the reaction wheels, spin them down a little bit, and to compensate for all of these other gravitational forces that are perturbating that orbit.
Okay.
Oh, I can see everybody's faces now. That's good.
Dennis, is there any are there any dangerous particles in that, like meteorites, anything that could impact this telescope?
Oh, absolutely. Got to remember, unlike Hubble, James Webb is pretty well exposed, and interesting enough. I think I covered this in the discussion of Webb itself. We've got those 5 layers in the sun shield, and at first glance, it looks like those layers are all parallel, and they are not. And that's intentionally, such that if a micrometeor goes through, it'll certainly go through all 5 layers, no problem. Remember, these layers are less than the thickness of your hair, right? But what we don't want is so as the sun changes position, now we're not going to get this straight beam of light that goes through the sun shield, and so no, micrometeors are going to be an issue, and hopefully there aren't going to be a lot of them. Of course, we could get hit by a big asteroid too, but I think the chances of that is pretty low. Yeah, any other questions?
I was wondering, when the telescope is fully commissioned, what the plans would be for their first targets.
Boy, everybody is asking that question. No, it's a great question, because everybody wants to know what the first data is going to be, and boy, they are keeping that pretty. I guess they don't. There's so much left to be done that think they clearly have a top 10 list already, but I'm not aware of it. And I think as we get closer to that, remember, we're at day 64. We've got another 120 days before we take our first data. And so once we get this next 54 days worth of focusing done, we now have to start calibrating the instruments and cooling them down and getting all of that working. And so yeah, we still have another 120 days of work to do before we do the first measurement.
Keep in mind too that whatever.
Oh, I lost you, Jeff. Can everybody else hear Jeff, or
I cannot.
No, we lost him.
we lost him? Okay.
You got a paper with a pen to write him a note, Dennis?
No, we got a chat. We can open up the.
Whatever that top 10 list is, it's got to know.
Oh, I caught something about the top 10 list.
Sounds like he's intermittent.
Yeah.
Can you hear me now?
Yeah.
All right. I don't know if my connection dropped out for a second. No, what I was going to say, I just was making a comment that, whatever that top 10 list of first things that they may want to go after, it also has to be visible from where we are in its orbit, and right. So
Yeah.
there's so many things. I bet even they don't know what they're going after.
Yeah. Well, but you'll like this, Jeff. Very, very high on their list. What they are willing to commit to is exoplanets.
Oh, for sure. Yeah. I mean,
that's really pretty high on their list. And there's a little misconception. Webb isn't going to be looking for exoplanets, so we're going to feed Webb exoplanet coordinates, and especially with its coronagraph. They're looking to find more exoplanets around known stars that maybe we can only see 2 or 3 exoplanets, but with the coronagraph they'll be able to see all of the planets that are around a particular star, parent star. And of course they'll be looking at the atmospheres as well. Any other questions?
Yeah, on that front, I was also just curious, given that it's on or how much of it's on the infrared end of the spectrum, how much of it will also just be pointing somewhere in the sky? Well, I guess I say sky, out into space, seeing stuff they hadn't seen before.
Yeah. Well, like Jeff says, it's all about. We are doing. We are orbiting the sun, right? So we're in a heliocentric orbit. So, and obviously, Webb actually can tilt up to like 25 degrees, and so it just has to make sure it stays within its shadow margin. And if you notice on Webb, I don't know if you can see it on my background picture, but there is a kind of a black apron around the segments to block light coming from behind Webb, and so it doesn't hit the secondary mirror. But so no, there's no shortage of things to point to. Going completely around the sun and being able to tilt up and down, 25 degrees.
Hey, Dennis, I was going to ask, so if I understand right, the focusing that you were talking about versus the alignment, is it right that the way the segments focus is by changing the shape of the mirror, and that the alignment is the tilting, the rolling, and et cetera? Is that right?
Yeah, well, basically, though these mirrors were as precision as we could possibly make them on the ground, right? But even these mirrors, which are beryllium, basically are shrinking, and they will stop shrinking at about 100 degrees Kelvin. When they get down that low, beryllium won't change its shape anymore. And so, yeah, so the kinematic or the roll, tilt, and pitch, and the X and Y are probably more for converging all of the mirrors into one focal point, into one star, right? But we have nice control over the I forget the range. It doesn't sound like much. It's like from a millimeter to so many nanometers, but we will be actually changing the curvature of each segment. So yeah, there's going to be the movement to get all of the stars to converge are going to be a fairly gross pitch, roll, and yaw.
Yeah, but I guess where I was going is does the sensor itself actually move fore and aft like our telescopes do as well? Or is it just the curvature of the mirror is what's focused?
Oh yeah, no, it's just it's all mechanical. It's all in the positioning of the mirror itself.
Yeah.
Yeah. Now we do have that fourth mirror, which is that fine guidance or steering mirror. That will in fact make subtle adjustments. And remember, the other thing that's kind of cool is the secondary mirror doesn't change its curvature, but it also has 6 degrees of freedom as well. And so there's 6 actuators on the back of the secondary mirror. Any other? Mitzi, no questions tonight? Come on, now you usually have 50 questions.
No, but thank you for the presentation. I thought it was very interesting how, in particular, you were talking about the L2 prime point and also the rotation of the individual mirrors.
Yeah. I don't know. I don't know why I found the whole story about L2 prime as being interesting, but I don't know if anybody else found it interesting. But I mean, we're so used to accepting what the media tells us that we're orbiting around L2, and we're just not doing to the first approximation we are, but not after that. Oh, I saw a hand go up. There's a hand in my face. Is that
how far
somebody?
how far is the telescope from Earth? Miles?
930,000 miles, almost 1 million miles.
So, and if the orbit on around L2 is almost 1 million miles too, you said, right?
Yeah, well, it's basically swings from closest point to L2 is about 150,000 miles, all the way up to 500,000 miles.
So it's almost as big as the distance from the Earth. Not quite, but maybe,
but only perpendicular.
right? Maybe a fourth of it, but it's significant.
Oh, I think that's an amazing piece to the story, and the fact that it takes 6 months to make just one complete orbit. So,
Dennis, I think
Yeah.
I asked this before, but I forgot what you mentioned. For these satellites that we put around L2, like Gaia and that, what's the exit plan? Once this thing runs out of fuel, what happens to it? Does it just float out into space, or what
Yeah.
happens?
Yeah, okay, so picture that saddle. That I think that's really the answer. Depending on where it's at. If once it can't maintain that orbit, depends on where it is in the saddle, on which way it's going to go. And more than likely, because all these Webb in particular, basically is so far in front of L2, that more than likely, when Webb runs out of fuel, it's going to decay towards Earth. So it won't drift away because it's on the good side of L2. Well, I don't know if that's the good side or not in that case. But if it was farther beyond L2, then it would drift out into outer space.
So what I'm hearing is that it runs out of fuel, it's going to drift back towards Earth, and we're going to refuel it.
Yeah, I would love to say that we could do that, but they
Send her back out.
Yeah, they never made any design changes for that. So, but the good news is, as of today, looking at the fuel gauge, and then projecting. Remember, I said there's going to be a correction to the station keeping every 21 days. So the good news is we are now approaching a little over 18 years in mission life. And so that's a far cry from, remember, the worst case is if we had to do lots of course corrections and we didn't get into a proper L2 orbit and we had to do additional burns. Remember, the low end of that number was 5 years. And everybody got pretty upset with that number. $10 billion for 5 years. That didn't seem like a good deal. And then after the first correction burn, the MCCA 1 burn or whatever, that estimate went up. And then after the second burn, it went to 10 years. And then we had to only do a 297-second burn. That we only needed to do a delta V of only 1.5 meters per second on the last burn, and which was nothing. And so that's when we revised the mission life to being approaching 20 years. So that'll be a good return on our investment. All righty. Well, this will be posted on YouTube in a day or two. And so, and like always, if anybody has any questions, feel free to contact me directly or email me. It's just good old dennis.roscoe@gmail.com.
Great, thank you.
All right.
Thanks, Dennis.
Thank you, outstanding.
Yeah.
Very
See y'all.
great.
Yeah.
So,
Thank you, Dennis.